Good afternoon, everyone, and welcome to this week's seminar. Happily, we have Alison Mitchell, who will present some of our research work, research results to us. And I'll give Willis the opportunity to introduce her, and then we can go ahead with the talk. But before that, Alison, do you want to try sharing screen?
Yes. Here it is. Okay. So this should be my slides. Do you see them full screen?
Yes, it looks nice. So you'll be speaking to a group, the astronomy group at University of South Africa, and we're made up of senior people, postdocs, and lots of students in different areas of research. Some do galactic science, some people do extragalactic science. So it's a mixed group. Some actually work on masers as well, and so on. So just some heads up about the group. Willis, please, can you go ahead with the intro? And then you can start, Michelle.
Thank you very much, Prof, for the opportunity. And now it's my pleasure to introduce Dr. Alison Mitchell. We met in Germany when they invited us for a conference. So Dr. Alison Mitchell is a researcher in the field of gamma ray astronomy, that's in energy astrophysics. Her research is focused on understanding the nature and origin of energetic cosmic rays that permeate our universe and continuously bombard Earth. In 2021, she took on the leadership of DFG-funded Eminotha Group, which is based at the Erlangen Center for Astroparticle Physics. Her group's focus is on unveiling the origin of cosmic rays by exploring pulsar environments at the highest energies. Her career has spanned several prominent research institutions, including the University of Zurich in Zurich and the Max Planck Institute for Nuclear Physics. She also contributed significantly as an assistant project scientist for the Cherenkov Telescope Array, CTA, where she worked in parallel to her postdoctoral research in gamma ray astronomy. She completed her PhD at Heidelberg University, earning a distinction with research that focused on pulsar wind nebulae and telescope calibration, conducted in collaboration with the HESS and CTA. Please join me in welcoming Dr. Alison to present to us today on the topic of investigating the origin of galactic cosmic rays with gamma rays. Thank you very much, Alison, for accepting to speak with us, and welcome.
Okay, thank you very much, Willis, for that very nice introduction. I'm really happy to join you today, albeit just online for now. And thank you also for the invitation to speak. Hopefully you can hear me well and see the slides full screen again.
Yes.
Just let me know if something is not working. Okay, good. Then I will make a start. So my talk today is on investigating the origins of galactic cosmic rays with gamma rays. And I hope you can see my mouse as well. Oops, this seems to have jumped. The cosmic ray flux covers many orders of magnitude in both energy and flux, and it covers nearly a perfect power law. This faint green dotted line is a perfect power law, and there's a couple of small deviations that we see from this, which are interpreted as hinting at the origin of particles of different energies. So we think there's galactic sources, up to about 10 to the 15 electron volts, and then extragalactic sources responsible for higher energy particles. And we can translate this into what energy we expect particles to reach in different environments. So this is shown via the plot on the right here. This is a so-called Hillas plot after Michael Hillas, who first realized that the maximum energy a particle can reach depends on its charge, on the strength of the magnetic field, and the size of the region. This is due to the gyration of particles in a magnetic field. So their Larmor radius for a given field strength must be less than the size of the source for them to remain in the region and continue gaining energy. So this gives us a maximum energy, and we can see, okay, for 1 PeV protons, which are thanks for turning the mic off. Supernova remnants are a good candidate. They have a lowish magnetic field, but a pretty large size, which compensate, and they can reach this solid line of 10 to the 15 electron volts. If we want higher energies, we need perhaps more extreme sources. Okay. Oh, sorry, one last thing I should mention. I will be using the word pevatrons occasionally in this talk. This refers to accelerators of particles to energies of 10 to the 15 electron volts or higher. So pevatron because they reach 1 PeV. Okay, so let's have a brief introduction to very high energy gamma ray astronomy to make sure that we're all on the same page. Gamma rays can be produced from a variety of physical mechanisms. And depending on the particle population, if it's leptonic like electrons or hadronic like protons, we have different emission processes. So from electrons, we expect synchrotron emission, which extends from radio up to X-ray, so across a large region of the electromagnetic spectrum. And then in the gamma ray regime, we have inverse Compton, which is the upscattering of ambient photons, such as the CMB or other radiation fields, by energetic electrons. And this produces gamma rays. From protons, they also have synchrotron component, but proton-proton interactions produce large numbers of pions, both neutral pions and charged pions. The neutral pions decay very rapidly into gamma rays, and the charged pions can decay to produce neutrinos. If we see neutrinos, it tells us there's a hadronic source there, but we need a lot of target material for that. And so we have this characteristic pion decay feature here from the rapid decay of neutral pion particles. So these are the general scenarios how we produce gamma rays from energetic charged particles. And then the next part of how to study them is from detection mechanisms. We need some kind of detector for this. And there's two main detection methods that are currently in use. These are water Cherenkov detectors, shown here by these box-shaped objects, and IACTs. So when a gamma ray enters the atmosphere, it generates a shower, a cascade of particle interactions that are moving very energetically through the atmosphere. And these air showers, when they pass through particle detector arrays, they produce Cherenkov light in water because the particles are moving faster than the speed of light in water. That produces this blue emission that can be detected. And these telescopes at lower altitude, they work in a similar way, but using Cherenkov light that is produced in the atmosphere from particles in these air showers. So to detect this faint light from air showers, for these telescopes, it needs to be very dark. But because the water Cherenkov detectors, these boxes up here, they're closed off, they can operate continuously, also in daytime, because they just measure within the dark box itself. So these are our two main detection methods. And why do we use both? Well, they're kind of complementary. So on these plots, this is a trade-off between what we call the sensitivity and resolution. And on both sides, lower is better. So this is as a function of the energy of the photon, the gamma ray energy. And the Cherenkov telescopes, so these telescopes on the ground that only work at night, they follow a flux curve like this and a resolution curve like this. What is interesting is the comparison to water Cherenkov detectors. So these boxes, they have a good sensitivity at the highest energies, and they can also operate continuously. So they're survey instruments, but their resolution is much worse. It's much higher on this plot. And then the third component here is satellites. So this is if we actually have a satellite above the atmosphere that can detect gamma rays. They have a a maximum energy limit. So you see the energy range doesn't go as high, and that's because we have a limit as to how large we can build satellites to actually detect gamma rays. So where are these facilities? There's a large number worldwide right now. There's a number which are Cherenkov telescopes on the ground, some which are going to be built in the near future, and some which are water Cherenkov detectors. So the ones which I'm going to mention today are mainly just working from left to right. Okay, Veritas, which is ICTs. There's HAWK. This is a water Cherenkov detector array in Mexico. Then we have 2 experiments which we're planning to build in the near future, both in Chile and South America. And then the one that I work with the most is probably the HESS telescopes, which are located in Namibia. And this is a photo of them there for scale. And then also LASO has become a big player recently, which is located in China, close to Tibet. Okay. So this is roughly where these experiments are located now. And then we have the gamma ray sources themselves. So within the last few years, we've seen a large growth in the number of sources. So this plot on the left just shows the number of sources we know for different energy ranges as a function of time. And we see the gamma rays at TeV energies, so these very high energies. They started around 1990, and we're now reaching of order a couple of hundred sources. So far below the number of sources we know due to satellites or in X-rays, but gradually gaining. And then these pie charts show the origin of these sources. For extragalactic sources, I'm not going to talk about these as much, although I think quite a lot of people here may be more familiar with AGN. These are mainly AGN, active galactic nuclei. The galactic sources, the largest category here is this light green one, which is unidentified. So for about half the sources, we still don't really know what they are. And then the next largest one is pulsar wind nebulae that I will talk about a little bit. Okay, so this is the HESS view of the Milky Way galaxy. So being in the southern hemisphere, it has a much better view of the Milky Way galaxy than I would have here in the north. And we see a large number of individual sources popping out of the plane. And these are, some of them are supernova remnants. So if I flick back and forth, you can see they have this sort of shell type structure. It looks like a ring. These are supernova remnants. We have a number of pulsar wind nebulae from these green dots. And then these composite systems are ones where there's both a supernova remnant and a pulsar wind nebula. And they're both contributing to the emission, so we can't disentangle them. And you see this doesn't cover all of the sources that are in the map. There's also one here, some around here, where we don't know what they are, or at least they're not in one of these 3 categories. And we can compare the galactic plane in different wavelengths. We have here the optical band on the top, then there's gamma rays with Fermi, and then as you go down, this was a prediction for pion decay from neutral pions that produce gamma rays. But if we have neutral pions, we also have charged pions, because pions of both types are produced in proton interactions. And if you have charged pions, you have neutrinos. So the IceCube collaboration in 2023, they published this detection of neutrinos from the galactic plane at 4.5 sigma after 10 years of collecting data, which was a nice result. So we know there must be hadronic accelerators in the galactic plane. Okay. So the first source class I wanted to talk about in a little bit more detail are supernova remnants. So these are explosions following the death of a star, the supernova, and the remnant is what is left afterwards. Now in supernova remnants, they have this blast wave shock that expands into the surrounding medium, and there can be particle acceleration at this shock front as it expands. So this is an image of a supernova remnant from HESS, and it's expanding outwards like this. And if we estimate a typical explosion energy of 10 to 51 ergs, and 10% of that goes into cosmic rays, and a typical rate of 3 per century, that is sufficient to explain the cosmic ray flux. But when we look at what we've actually measured from supernova remnants, so these ones which peak around a GeV, ones over here that peak above a TeV, and then some young ones, but actually have a lower flux. Not many of these supernova remnants seem to actually reach a PeV that we need to explain galactic cosmic ray acceleration. Galactic cosmic rays should reach these PeV energies. And that seems to not be present in supernova remnants so far. A second option we have, though, is it could be that cosmic ray accelerators only accelerate up to a certain limit, a maximum energy, and from that time onwards, the cosmic rays escape the source. So maybe they reached a PeV, but in the past. And if that is true, the particles will have escaped, they travel through the medium and interact with surrounding clouds. They don't stay at the supernova remnant. So perhaps that is something which actually happened. That means we can use gamma ray emission from nearby clouds to test and search for pevotron activity that may have happened in the past, which means we can even expect a new population of passive sources, these illuminated clouds that emerge at the highest gamma ray energies, because it's no longer particles at the source, they've escaped, but they illuminate some target nearby. And the spectrum of particles at the cloud can therefore be different from that at the accelerator. And so we set up a model. We don't worry too much about these equations, but we set up a model for the energy dependence and also for the particle release and evolution. So if particles of different energies are released at different times during the supernova evolution, there's a time dependence here. So this just to the power of minus 1 over beta means that it decays over time. So this is the momentum, meaning the particles of a given maximum momentum, they can gradually escape. And then we have supernova remnant evolution. The radius expands over time, and how it expands goes through different phases, i.e. it gradually slows down, which you can tell from the slope of this curve. It gradually becomes less steep, so the expansion slows down through different phases of evolution. So if we put all of this together, we have a model for the evolution of supernova remnants, firstly. And if we make the assumption that all supernova remnants act as pevotrons for some time, which basically means we set this maximum value to be a PeV, and then we can look at different known, well-studied objects and see what emission we expect now. And we explored this in our model. We could match the model well to data for known supernova remnants. We did an MCMC fit. And here on the right, we show the expected emission compared with the sensitivity of a future detector, this WGO. And we see that we should be able to detect several of these systems. Now, once we've had this acceleration, the particles can then travel through the surrounding medium to reach the cloud. And then we also need to describe the interactions with the cloud. So the first part is this transport through the surrounding medium. The main properties here, we have a diffusion radius that depends on this d of e. That is the energy dependent diffusion coefficient, and also on time. So how far you diffuse increases the more time you have. And this energy dependent diffusion coefficient has an additional factor chi, which is for suppression in different media, the magnetic field, and some term which describes turbulence. So in general, this diffusion is suppressed in the vicinity of accelerators, and this is what we actually see experimentally. So this was a model targeting one source where the typical values measured independently for diffusion are these blue lines, and what we measured in the vicinity of the source is this red band here, with the uncertainty shown with these bars. So the diffusion in the vicinity of an accelerator is much lower than the average in the surrounding medium. Okay, so what does this mean for our model for the expected emission from clouds? We can look at the dependence of the gamma ray flux, so this time here on the left, on different variables, and we can see, okay, let's test the dependency on the age of the supernova remnant, the density of the cloud, and the distance between the SNR and the cloud. So the first one, the order of the plots is slightly different from the text. The first one on the left here, this is actually the cloud density. If we have a higher density, there's more flux. There's this density term which directly scales with the flux, and we see that here in the plot. The next one is the distance and the flux, this F. And if we go back a few slides, we saw that this F depends on the diffusion radius, this RD term. So if it's closer, you reach the source sooner, and the peak will gradually shift to lower energies. If it's further away, it takes longer. So the higher energy particles, the ones that escaped earlier, are the first to arrive. And the peak will gradually shift, increasing and going towards lower energies. The third one is the age. And here I said the peak shifts to lower energies for all the supernova remnants. So if it's young, you have the most energetic particles arriving first. They lose energy, and over time, lower energy particles reach the cloud, but later. So this peak shifts towards lower energies. So this seems to match the behavior we expect. And we did a study where we applied this model to known supernova remnants and clouds in the galactic plane, and we compared to data. So here, the colored circles, the solid colored circles were our flux predictions for which clouds should be illuminated by supernova remnants. And then the contours are from Hess. And the red circles are from LASO, this Chinese facility. And we can see, okay, there's some mismatches and some coincidences. So in some cases, our model is likely not appropriate, but in others, we seem to have some flux which matches the location and or the flux of other sources. This can also be applied to individual sources. There is, for example, one which has emerged at the highest energies, LASO J2108, where there's no associated accelerator. We just see gamma ray emission, there's a cloud, but we have no idea what the accelerator is. And the only thing which is in the vicinity is a cloud. And so we tried to apply this model. So we inverted the argument. If this source is a cloud that has been illuminated by a supernova remnant, what properties should the supernova remnant have? We found we could do this. There's observations of the cloud, so we know those properties, we can fix them. So instead of changing the density this time, we look for what properties the supernova remnant should have. And so we did this changing, on the top here, we changed the age of the supernova remnant. And so the darker, the younger, we find it must be young. And here the distance of the supernova remnant to the cloud. Larger distance, lower flux, we see that it must be fairly close. And this is essentially the conclusion we came to for two different molecular clouds that were studied. The models that best matched the data had a fairly low distance. It needed to be around 50 parsecs away or less, and a young age, so less than 10 kiloyears and better less than 5. Okay, now if we look at the highest energy sky, as seen by LASO, this is a water Cherenkov detector, which from our sensitivity curves, they have a much better performance at the highest energies. They see a large number of sources, 43 sources now above 100 TeV, with a significance above 4 sigma. Now in 2021, we only had 12 sources above 100 TeV, and in 2016, we had the first ever. So this is really fairly new results. We now have, we're getting on for nearly 50 sources above 100 TeV now. And it's really thanks to these new detectors. And the interesting thing about this is we were hoping that they'd be mainly supernova remnants, but actually at least half of them are potentially associated with pulsars. So that's the next source class I want to look at. It's pulsar environments. So what's happening around a pulsar? So these pulsars, these are compact, rapidly rotating neutron stars. Most of the highly energetic pulsars in the LASO visibility region have associated gamma ray emission. And we can look at, okay, there's a couple of odd exceptions. I should explain here. The red dots are pulsars where we see emission of about 100 TeV. The triangles, these blue triangles, these are pulsars where we see TeV emission. The green squares are pulsars where we haven't seen anything yet. And then the y-axis here, this is the amount of energy loss and the distance from Earth. So it's energy loss versus distance. If it has a higher energy loss or if it's closer to us, we can expect to see it. So the sensitivity goes roughly as a diagonal line. There's a couple of interesting exceptions. Like presumably here the distance estimate is wrong and it's closer than this large distance. This one is odd, perhaps we just haven't looked for long enough to actually detect it. But what is going on to power this? Well, pulsars, these are rapidly rotating neutron stars. They have a very strong magnetic field. So it's rotating this way. We have magnetic field lines here forming the magnetosphere. And the magnetic field induces an electric field on the surface, which can accelerate charged particles. So these charged particles, accelerated in a magnetic field, will produce radiation. Then this radiation and charged particles, they stream out along magnetic field lines, and the radiation produces electron-positron pairs. So you have gamma ray pair production, or rather photon pair production. These pairs then produce more radiation, so curvature radiation, whilst on the field lines. And we have a cascade process, and then we have, at a certain region beyond, the wind streams out, it forms a shock where it slows to the sound speed of the ambient medium. And we have this non-thermal nebula, which is of high energy particles, and this is mainly electrons and positrons due to this cascade pair production process happening here. So this is essentially a pulsar, wind, and then we have the nebula. So they're called pulsar wind nebulae, or a PWN for short. To get even more complicated just for a moment, we have this pulsar wind nebula here. Is expanding typically within a supernova remnant because the pulsars themselves are formed during a supernova explosion. So we have the supernova remnant and then a pulsar wind nebula inside that expanding. Now when we reach this stage 2, the systems can interact with each other and disrupt the shocks, which can lead to some particle leakage. These are these lines coming out here. So we can have some particle leakage in the region. And then at late stages, we can even have a large halo of escaped particles in the surrounding ISM. And so just for scale, this compact part and this central part shown here in the dark blue, we refer to as the pulsar wind nebula. But once we have escaped particles, it's really a halo in the surrounding medium. Now, this diagram is based on our understanding, but in gamma rays, what we see is a bit less precise. We see something which is more like a big blob, to be honest. So we have here the Crab Nebula, a well-studied source. You may recognize the optical image I'm about to show you. And then we also have Vela here and Gaminga. These are fairly well-studied systems now. So the Crab Nebula is shown down here on the right. This is a much more well-known image of the Crab Nebula that you may have seen before. In gamma rays, it's just this blob. But it's quite a spectacular source, very bright. And we do actually see gamma ray emission here. The black dots are from the Crab up to 1 PeV, which is quite exceptional. From Vela, these are the blue line. We see the entire curve, this dip and then peak. That's the synchrotron and then inverse Compton components. This is all shifted to slightly higher energies. I think that's because its energy output is very high and it's also very close to us. And then we also have MSH 1552, which is a bit like the Crab, but a bit lower down. So we have this PeV emission near the Crab, or from the Crab, sorry. Okay, so now we have these electrons produced. When I say electrons, I mean electrons and positrons that are produced by the pulsar or from the radiation, expanding into the surrounding medium. And then what happens is as they travel away from the pulsar, they cool. So what do I mean when they say cool? Here, this is another pulsar wind nebula, as seen by Hess. The pulsar itself is marked by this green triangle. And what you see is as we change the energy range down here on the bottom right, the extent of the emission changes. So at the highest energies, it's a small part very close to the pulsar. And at lower energies, it's much larger. And that is because the particles lose energy as they travel outwards. So you don't have the highest energy particles at large distances because they cool, they lose energy. And this can also be seen in terms of the spectral index as a function of distance. It typically increases with distance. So that means the slope is changing. We have fewer high energy particles at large distances from the pulsar. And this is what we expect for a leptonic source. So this shows us that these are leptonic particles, not hadronic, that dominate this emission. Now a typical halo or archetypal halo is then the Geminga pulsar, where it's diffused into the ISM. The pulsar is traveling with some rapid motion, and the emission itself is quite large. It has typically slow diffusion, but this is much below the galactic average. Okay, I think I can skip the next slide for that. Okay. The third source class I want to talk about is stellar clusters. So stellar clusters are groups of many stars, and as they're typically formed from the same gas cloud, these star clusters all have a similar age and they're at the same distance because they're all from one cloud, and a similar chemical composition because that's just from the parent cloud. And we can have some massive stars in these regions, each of which has its own stellar wind, much like our solar wind, that blow outwards. Now, these winds can combine from many stars in the cluster to make a collective wind that drives some shock into the surrounding interstellar medium ISM. This typically requires quite young systems or star-forming regions, and some of the highest energy photons that we've measured to date of order PeV are actually from stellar cluster regions. Just one or two, they're not as numerous, but very powerful. So these two schematics show essentially the same thing. We have some stars in the center here. There's a radius of the cluster, this RC. And then in this region, this is the shocked stellar wind. So much like we had for the pulsars, but here on a larger scale, we have a wind which is expanding into the surrounding medium. We have some termination shock. And then here we have what we refer to as the shocked wind, or bubble, or in the case of pulsar nebulae was the nebula, but here it's quite similar. It's a bubble here created by this wind. And outside of that, we have the interstellar medium. So we try to apply a model to known stellar clusters to try and predict their gamma ray emission. And for this, we used the Gaia DR2 catalog of star clusters, which is publicly available. And we selected those with young ages less than 30 megayears. And we wanted to answer the question, which stellar clusters are the most promising Pevatron candidates? It's not just this Cygnus cluster, but others as well. Now, in order to estimate the physical properties that characterize the stellar clusters, we needed to know the mass of the cluster, as well as the luminosity and the radii. And this turned out to be kind of tricky to estimate. We did end up doing a separate dedicated study to try and estimate the mass of these clusters, and this shows our distribution in log scale. So you can see typically they have masses of order hundreds to thousands of solar masses. And here, the maximum mass that can exist in the cluster depends actually on the age of the cluster, because stars of the highest masses, so of order 150 or 100 solar masses, won't live as long. They will quickly burn and then die, typically becoming black holes first. And then this age-limited maximum mass will, of course, gradually decrease over time as stars of different masses use up their fuel. So we use this mass, luminosity, and radius as input to our model to estimate the expected cosmic ray and gamma ray flux. And because we gradually have more and more contribution from supernovae, we can see here the expected gamma ray flux on the y-axis, just concentrate on the solid lines, the contribution over time. This gamma ray flux from the wind increases and then starts to drop off because the wind gets disrupted from the supernovae that occur within the cluster. And after a couple of mega years, the supernovae actually end up dominating the expected gamma ray flux from the wind. So we just see the collective effect of multiple supernovae rather than this wind. Okay, so we applied this model to a selection of stellar clusters. And the key thing here is the gray band on the left. This is for one cluster, Westerlund 2. And we see there's a large uncertainty in our model, unfortunately. There's a lot of freedom with different parameters, and we can match the data, but there's a lot of tuning that could occur here. Despite this, we tried to estimate our minimum or baseline scenario and our most optimistic or maximum scenario for a set of stellar clusters. And that is what's shown on the right. I appreciate there's quite a lot of lines here. The solid lines are then the lower bound, and the dashed lines of the same color are then the upper bound to the flux. So this gives us a range in which we expect the flux from a given cluster. The top right might be easiest to see because we have this blue line and blue dashed line for Dolice 3, and this green line and green dashed line for Ruprecht 44, and then sensitivities of different instruments. So we use this to try and make some predictions. And this variation in the different estimates, this comes from whether or not we include the supernova contribution, so this dashed line, whether or not we account for an underestimate, a systematic underestimate in our cluster mass, etc. But we see reasonable agreement when we compare to individual clusters. Okay. Now, the last couple of types of sources I want to talk about, firstly, white dwarfs. So obviously that's not neutron stars. These are the end products of even lower mass stars, and particularly in binary systems. If we have white dwarfs in binary systems, we can have what's known as a nova. So if you look at this plot on the right, if you have two stars of different masses in a binary system, one will typically end its fusion process first. It will let go of the outer layers, it's a nebula, and become a white dwarf. But in the binary system, the other star could still be in the main sequence phase, or if it's slightly more evolved, it could become a red giant. Now, the white dwarf being a compact object, this can accrete material from the main sequence star. And once it accretes sufficient material on the surface, this can ignite nuclear fusion burning on the surface of the white dwarf, which gives us a thermonuclear explosion. If we see this once, we refer to it as a, classical nova. And if we see it multiple times, we refer to it as a recurrent nova if there's been more than one outburst. And if it's coming from a system with a red giant, it's also known as a symbiotic nova. So this is just rough terms we use for classification. And this is provided that the total mass on the white dwarf remains less than 1.4 solar masses. If it's even brighter than that, then we end up with a type 1a supernova. So when a nova occurs, we have a dramatic increase in optical brightness, to the point where you can even see some of them with the naked eye. And the typical duration is of order weeks to month. So this actually happened in 2021 from a binary system comprised of a white dwarf and a red giant at about 1.4 kiloparsecs away. It's a quite well-known system called Arecife-Yuki. The last two explosions were in 2006 and then 8th of August 2021. We got lucky that it exploded when Hess in the southern sky could also point at it and look at it. And it was detected by gamma rays over order of days to weeks. So on the right, we have the gamma ray map from the first 5 days, 1 to 5 days here, and then between 2 to 4 weeks after the initial outburst here on the right. So this curve, this light curve over time, shows the increase in optical brightness that happened in August 2021 that then dropped off again. And when it was above this dashed line, the magnitude was less than 6, so it was actually visible with the naked eye. So if you knew where to look for those 2 weeks in August 2021, you could have looked up in the night sky and seen a new star. And this was a pretty exceptional event. It reached a factor 100 times higher energy than has been seen in other novae at the time, which meant that we could detect it in gamma rays from the ground, and it was the first time we'd ever done this. And this gamma ray evolution, this changed over time as we saw from the sky maps. One was less bright than the other. And we see this also in the light curve. So we have Hess here in red. It peaked at around 4 to 5 days after the optical peak. And we have Fermi-Lat, which is the satellite shown in blue, and that peaked after just over 1 day. So it shifted slightly. So we see the peak flux in the GeV range was earlier, but the maximum energy from the acceleration was after 5 days. So here we have the green curve from night 1, the 9th of August, and the orange curve from night 5, the 13th of August. And we see that the peak in the GeV shifted down, but the maximum energy actually went up. And this showed us that it takes time to reach the highest energies from these shock acceleration processes. And this gave us a new type of cosmic ray accelerator that a HESS collaboration published in the Science Journal. And we're actually right now expecting the next one to explode soon. This is T Coronae Borealis. It's expected to explode in 2025, and when it does, it's likely to be bright. So if you hear that this one has gone off, you have about 10 days to a couple of weeks to go outside and look at it with the naked eye. It is currently visible from the southern hemisphere. It will be from end February, start to March. It's just about visible again until November. So if it explodes sometime between now and November, do go outside and see if you can spot it. It only goes off once every 80 years, so it'll be a once in a lifetime event. Another type of binary system, which has been recently established at very high energies. Again, here's a paper published in Science from the HESS collaboration. These are microquasars. So microquasars, as the name suggests, they're like miniature versions of the quasars that we have from active galactic nuclei. So they have a much smaller black hole, it's stellar mass scale, but they also show these jets. And SS433 is quite a known system in our galaxy, which has it's a binary system of a black hole and an A star, and it has these powerful jets. These are the blue contours, or on the right, these cyan contours going outwards. So here, this green emission is the radio, and this was the supernova remnant, but you can see it's actually become distorted by the presence of the jets. The contours are the X-rays, so this is the actual binary system, and then we have the X-ray jets extending here. And then what we see with HESS is actually the emission along the jets changes energy. So the highest energy emission is found at the base of the jets, closest to the black hole. And then as we move outwards or go down as we move outwards, the energy goes down, or as you go down in energy, the emission shifts outwards. So that shows you have emission which is cooling along the jets. And this can be used to constrain the velocity with which the particles were launched, and also provides indication again for leptonic emission from these sources. Okay, so that was a whistle-stop tour of several different source classes. I want to just conclude by giving you a brief outlook into what is coming next. We have future facilities coming along and some challenges. So upcoming facilities, we have CDAO, which is going to be these Cherenkov telescopes on 2 sites. The Northern Hemisphere in La Palma, which is technically Spain, but at the same latitude as Algeria, it's level with the Sahara Desert. And in the Southern Hemisphere, the site in Chile. SWGO will also be in Chile, but at a different site, further north in the same country. You have ASTRI, which will be IACTs, and Alpaca, which will be a survey instrument, so more of these dark boxes of a slightly different type in Bolivia. And then the LASO, the Chinese facility, they plan to extend their site, so it's no longer just the Cherenkov detectors and scintillators, which are all types of dark boxes, let's say. They plan to enhance it with more IACTs. But we have a number of challenges. The galactic plane. So far, we see these individual sources, but there will be many more coming along, and they will overlap, which can be a challenge for us, because the resolution is not as good in gamma rays as at other wavelengths. We have joint modeling with multi-wavelength and multi-messenger observations. We want rapid response to transients, some robustness to observing conditions, and also big data and powerful computing approaches. There is one more challenge that we found recently. So together with my postdoc Sam Spencer and a master's student Thomas Lang, we looked at the effect of satellites flying overhead on the HESS telescopes. And this plot here shows within just half an hour of the HESS telescopes in the Namibian sky, we saw these 4 satellites cross the field of view of our telescope. And the rate of the trails that we see has been increasing over time from 2020 to 2023, end of 2023, when we published the study. See, here's the number of satellites being launched, and then the number of trails we saw are the black dots, and it's a lot of scatter, but an overall increase over time consistent with the number of satellites in the sky. So that could be an increasing problem, because although they are gamma ray telescopes, they detect this faint Cherenkov light, and that means they're also sensitive in the optical. Now, just to briefly provide some context, Willis already mentioned this at the start. We met each other at this workshop that was held in July 2024 on synergies in non-thermal astrophysics in Southern Africa. That's because beyond gamma rays and HESS in Namibia, I mean, HESS has now been there for quite a while. It will now continue until 2028. So we have a few more years still, but we will soon be superseded by CTA. There are nevertheless strong synergies with other facilities in Southern Africa, and we had a workshop hosted locally here dedicated to exploring this. So in particular, this featured SALT, which is the South African Large Telescope, the African Millimeter Telescope, which is likely to become part of the worldwide Event Horizon telescopes once it's built, also in Namibia. And then also in South Africa at the Tsaro site, we have, of course, MERCAT, which is a forerunner to the Square Kilometer Array, which is going to be a very powerful radio array coming soon. And this is what MERCAT currently looks like. Okay, so a summary. I gave a brief overview of several different source classes that are emerging at these highest energies, even larger than 100 TeV, which really implies the presence of these pevatrons or PeV particles. And surprisingly for us, at least, it's not only supernova remnants, which was what we thought in the past. We also have these pulse environments, we have stellar clusters, we now have novae and microquasars since just a few years, which is really surprising, and it's good to see this rich variety emerging at the highest energies. Now, I spoke a bit about this idea that the highest energy particles are also the first to escape from the accelerator, which means that they can simply leave, travel across the intervening medium, and first interact with nearby materials such as molecular clouds, which implies that it may not just be accelerators, but we can also even expect some population of passive sources emerging at the highest energies, which are clouds illuminated by accelerators. And this can help us trace back to search instead for past pevatron activity. So there's still a lot to study and unanswered questions. And I leave you with this, that's a photo of me with the PhD and postdoc members of my group. I also have some master and bachelor members, and this is a photo from our workshop last July. So I will have to go back to this mode now so I can actually see you. And thanks for your attention. If you have any questions, I'll be happy to answer them.
Thanks very much, Alison, for the wonderful presentation. That's eye-opening. Any questions?
There's one from Roque.
Yes.
Hi, it's Kevin. Thank you very much. I'm interested to know, is there any link between, I'm talking about pulsar wind nebulae, is there any link perhaps between what you observe in the gamma ray region to some of the things that we see in the radio regime, like nulling and mode changing? Is there any link with that, or are they just completely different emission mechanisms altogether? Do you know?
It's a good question because it depends what exactly you mean from the radio emission. Because you mentioned nulling, I'm thinking of the pulsed emission. And and we do see some pulsed emission also in gamma rays. They didn't really talk about the pulsed emission from the pulsar. So the pulsed emission really comes from the magnetosphere region, and it has to be released from this point. So there are some connections there. We see, I think it's now at least about 30 or 40 pulsars at GeV gamma rays, but at the TeV from ground-based instruments, we have, I think, 4 pulsars now, which are quite exceptional, but that they're really producing emission at TeV energies also just from the pulsation was a surprise, because we actually thought a lot of the highest energy comes from the fact that these particles get accelerated again at the shock front of the nebula. So they have sort of a second round of acceleration from the wind termination shock. So we also see radio emission from the nebula, which may then correspond to the TeV, in that we see the synchrotron and the inverse Compton from the same particle population. But in the radio, what is particularly interesting is that the beam that we see from a pulsar in radio does not always seem to match from the gamma rays. I don't have that plot with me, but if you look at some phasograms of the pulsation from pulsars at different wavelengths, it is sometimes not quite shifted between the radio and gamma rays, but you may not see the same two peaks, or you may not see the bridge. And this can be in some cases different behavior, which means it must then be coming from a different part of the magnetosphere. So the extent to which it's directly connected and or originates from a different location, I would say is not yet well known, because we don't have as many systems at the gamma rays that we've been able to study in as much depth.
That's fascinating. Thank you.
Thanks, Kevin. Any other questions?
If I can ask, it's Paul speaking.
Hi, Paul.
Yes, Paul.
Just thank you. I thought it was a really nice overview, and for us not familiar with the subject, very useful. So thank you. You spoke in your last slide about the sort of big unanswered questions. Just any comments on around what those big questions are in the field?
Yeah. Okay, so to unanswered questions in the field, I think we just touched on one with Kevin, which is to what extent the gamma ray pulsed emission is connected with the radio in pulsars. We see a lot of sources in the gamma rays where we still don't understand the origin. So a lot of this is, if I can go back here. So the first obvious unanswered question is the entire right half of this pie chart, which is what are these sources? Some of them there's more than one possible answer. Some of them, because we see more than one potential counterpart, some of them are like J2108 that I briefly mentioned here, which is what we call a dark source, where we see gamma ray emission, but nothing else in any other wavelengths. And then you have to try and explain that, right? Where is the emission coming from? In this case, it seems to be some illuminated cloud. What is, I think, very unclear is what energies can be reached, what's the maximum energy reached by which types of accelerator, and how do we reconcile that with the all-particle cosmic ray spectrum? As we know from the cosmic rays, galactic accelerators must reach PeV energies. But when we look in PeV energies or close to PeV with gamma rays, we see mainly leptonic sources rather than hadronic. So that also doesn't really explain what we're seeing, because there must be hadronic sources that also reach a PeV. So it's still a bit unclear which sources actually power the cosmic rays. And then for each source class, there's a lot more specific questions that you can dive into. For microquasars, it's really the physics of the jets. What is the launching mechanism? How are they formed? How do they process? How is the emission transported? How does the system change over time? For novae, when do they explode? Our best guess was 2024, plus or minus 2 years for T Coronæ Borealis. It still hasn't exploded. And then there's been revisions for mid-2025, plus or minus 6 months. We don't really know. We can guesstimate it, but it's, yeah, of order years here and there. For supernova remnants, theoretically, they should reach a PeV, but we've never seen that observationally. So that needs to be reconciled. And then for pulsars and pulsar wind nebulae, are there any hadrons in the system, any positively charged ions that also make it out? So it's not just electron-positron pairs, or mainly electrons, because the positrons don't survive as long. How are they transported outwards overall? At what point does that merge with the interstellar medium to become part of the all-particle cosmic ray flux? I could go on, but I feel like that's enough to start with.
No, thank you. That's a nice start. I can ask another question. I see there are no other hands up. That one slide when you refer to microquasars.
Yes.
I think two questions about that. What sort of masses are we looking at, both in terms of the black hole and the star? And the second question, you showed emission there, and I think you showed the contours are X-ray.
Yeah.
What other emission do you see from these microquasars? Do you see things in the radio, in optical, for example?
Yes. Yeah, good question. So I don't know if you can also see my presenter notes, because on this slide I just happened to have the sources for this image on the right in the notes. So the background here is indeed radio. So all of this sort of green wispy emission, not the conduct, but the green wispy emission is radio here. So the radio emission, it probably depends on the frequency, and I don't remember off the top of my head exactly which frequency. The radio which is shown here from this National Radio Astronomical Observatory, maybe that was Australia, I don't remember exactly. The frequencies they're using here give us the nebula shown on the right. It could be that if you look in a different frequency, you actually see the radio emission from the jets. That I haven't looked into, but that should also be present. We see it at GeV. The contours here are from the X-rays. The optical, I think we do see optical, but potentially just from the binary in the middle and not from the jets. From memory, I don't think we see the jets in optical. I think that's because it's mainly non-thermal emission, which essentially means synchrotron or inverse Compton. And the masses, that was it. It's a stellar mass black hole, so I want to say tens of solar masses, but I don't know the exact numbers off the top of my head. But of order, I would say of order few to tens of solar masses.
Okay, so thank you. That's sort of interesting information. I hadn't come across the term microquasars before. And having sort of something of that, no, those sizes, it's interesting with the level of emission from relatively smaller objects.
Yeah, this is kind of a little bit where some of my interest in these galactic sources come from, for both novae as well. Like novae act a bit like a scaled down version of supernovae, you could argue, but that means they also evolve more rapidly. So you can, in my opinion, study them in a bit more detail. You can know where you expect one to go off, and they're a lot closer. For microquasars, it's similar. SS433 is the first one, but we've now also seen V4641 Sagittari, which I think that was also published in the last year or so. And there's indications from LASO for another 3. So microquasar as a population have gone from, we see 1, which was new about 2 or 3 years ago in the gamma rays, to we see 5, maybe. No.
That sounds like an interesting field. No, thanks. Thank you for your comments. Appreciate
Thank you for the questions.
The answers and comments.
Thanks, Paul. Any other questions? Any other questions or comments? Okay, seems like there are no more questions, Alison. I just want to say thank you very much for the excellent account of the origin of galactic cosmic phase with gamma rays. Thank you so much for your presentation. And we hope you'll accept another invitation if we send it to you.
Thank you very much. It was my pleasure to talk about a topic that I'm very interested in personally as well. And if you like, I can send you the slides, perhaps. It would be interesting
Yes,
for
please.
people to refer to. Okay, I will do that. Thank you very much for attending today.
Thanks so much, Alison. Thanks everyone as well for attending the seminar. Thanks.
Goodbye. Have a good day.
Thanks all. Cheers.
Thanks everyone. Bye.